Which is faster, consciousness or the speed of light? This is physics' ultimate conundrum. According to Einstein's special theory of relativity, no object with mass can exceed the speed of light. But consciousness has no mass. Does that mean it can surpass light speed? When you think of the M78 nebula 1,600 light-years away, your consciousness can reach it in an instant. When you recall everything about your past, your consciousness can instantly return to those moments. Could consciousness truly outpace light? Now relax your body and close your eyes. Follow the reasoning of those brilliant scientists, and slowly pursue the ultimate answer to this final conundrum. Einstein's special theory of relativity established an insurmountable ultimate speed limit for our universe. The speed of light, approximately 300,000 kilometers per second in a vacuum. This figure is etched into the fundamental fabric of spacetime like an immutable cosmic law. No material entity carrying information or energy can attain or exceed this velocity. For as an object's speed increases, its mass grows proportionally. As it approaches the speed of light infinitely, its mass approaches infinity. This implies infinite energy would be required to accelerate further. Thus, any object possessing rest mass can only approach the speed of light infinitely close, never reaching it. This physical law seems to impose an absolute boundary on all motion within our universe. Yet human consciousness appears to be a rule-breaking exception. When we close our eyes and construct an image in our minds, our thoughts can instantly reach any corner of the cosmos. Take, for instance, the M78 nebula, shrouded in dust and gas 1,600 light-years away. Light traveling from there must endure a 1,600 Earth-year journey before reaching our eyes. Yet our brains can conjure its hazy radiance in the blink of a thought. Our consciousness can also leap through time in an instant. It allows us to vividly recall the sunlight and scent of a specific afternoon years ago. This sensation feels as though our thoughts have truly traversed space and time back to that precise point in the past. This intensely real subjective experience poses a sharp question. If matter cannot exceed the speed of light, can consciousness, which has no mass, do so? Which is faster in the universe, consciousness or light? The answer to this question seems to directly challenge the foundations of modern physics, and touches upon our understanding of the very nature of our own minds. If we assert that consciousness is a purely spiritual phenomenon, unconstrained by physical laws, then its ability to transcend the speed of light appears a reasonable inference. But if we regard consciousness as a product of the brain, a material organ, then it must obey all the physical and biological laws governing the brain. This creates a perplexing contradiction. On one side, the absolute physical laws that govern both the macrocosm and microscopic particles. On the other, the free mental experience each of us can personally feel. At this intersection of contradiction, we must embark on rigorous scientific exploration. We must simultaneously draw upon the most revolutionary theories in physics and the cutting-edge discoveries in neuroscience. Only then can we dispel the fog of subjective illusion to glimpse the objective truth beyond. And the starting point for all this is confronting the ultimate enigma itself. Which is faster, consciousness or the speed of light? The answer to this question is far more complex and exquisite than intuition suggests. It will lead us deep into two equally vast realms, the cosmos and the mind. Ultimately, it will reveal a harmonious unity of science and perception in a surprising conclusion. Please join me in a simple thought experiment. Now slowly close your eyes. Draw your attention inward from the external world. Imagine your consciousness breaking free from everyday constraints, soaring freely toward the depths of the cosmos. Your destination is a celestial object designated M78, hidden deep within the Orion Nebula, that expanse of interstellar dust and gas drifting through space. lies approximately 1,600 light-years from Earth. This distance means the light you see from it now began its long journey around the 5th century AD. When that beam of light departed the M78 nebula, the Roman Empire on Earth was slowly drawing to a close. Human civilization was about to enter a new era. This light journeyed alone through the void of space, traversing countless star systems and galactic spiral arms. After a full 16 centuries of arduous journey, it finally reaches your retina at this very moment, becoming a faint light signal. Yet, when you merely envision this nebula through thought, the entire process is vastly compressed. Your consciousness need not wait 1,600 years, not even a single second of physical time, to construct its complete image in your mind. You seem to see a luminous interstellar nebula, quietly rotating at Orion's waist, where young, hot stars illuminate surrounding dust, forming a beautiful blue reflection nebula. New protostars incubate within dense gas clouds, occasionally stirred by stellar winds into subtle ripples. This transcendent experience of time and space isn't confined to distant stars. When you suddenly recall a summer night scene from childhood, all those sealed sensory memories awaken instantly. You might remember the silhouette of that paulownia tree in the old family courtyard, the intermittent chirping of cicadas in the night breeze carrying summer's heat, the sweet, crisp scent of freshly cut watermelon drifting through the air, your grandmother's kind face, rocking in her wicker chair with a palm leaf fan. Though weathered by the passage of time, these fragments of memory become vividly alive the moment consciousness summons them. Your thoughts seem to unlock the shackles of time, transforming you once more into that child gazing at the stars. This mental journey through time and space extends equally to future visions. You can plan your life a decade from now in this very moment. Imagine yourself strolling through the streets of a foreign land, feeling the unique atmosphere and rhythm of an unfamiliar city. Though these visions are fraught with uncertainty, they too can unfold in your mind with astonishing detail. These everyday mental experiences create a powerful illusion, as if consciousness transcends the laws of physics, unbound by the speed of light, free to traverse every dimension of time. As your thoughts roam the cosmos, you might leap instantly from M78 to the Crab Nebula, to observe the remnant of a supernova that erupted in 1054 AD. Its light took over 6,000 years to reach Earth, yet your consciousness can behold its splendor instantly. You can simultaneously envision the majestic pillars of creation, the cradle of starbirth within the Eagle Nebula. Though it lies 7,000 light-years away, in your mind it feels within arm's reach. This ability to teleport our thoughts raises a question. If matter cannot exceed the speed of light, how can consciousness achieve such space-time leaps? Does consciousness truly possess some form of superluminal property? The answer to this question touches upon our understanding of the universe's essence and the core mysteries of human cognition. But please hold onto this curiosity about the cosmos. In our next exploration, we will unravel this puzzle together. You will discover the truth is far more exquisite than imagined. Now, let us continue this cosmic voyage of thought and delve into the scientific principles behind this wondrous experience. This experience of consciousness seemingly transcending light speed is indeed captivating. Yet the essence of scientific inquiry demands we look beyond surface phenomena. We must examine the objective facts behind these subjective sensations. Modern science has prepared a comprehensive explanatory framework for us. This seemingly contradictory phenomenon does not violate the laws of physics. To understand the truth of consciousness traversing the cosmos, we must employ two powerful scientific tools simultaneously. First is physics, particularly Einstein's theory of relativity, which explains why no material entity can exceed the speed of light. Second is neuroscience's research on consciousness and memory, which reveals the biological foundations of conscious experience. From a physics perspective, we will delve into the nature of spacetime, analyzing why the speed of light, as a universal constant, is an insurmountable barrier, examining the fundamental laws and limitations of information transmission. These studies will confirm the physical impossibility of faster-than-light travel. From a neuroscience perspective, we will dissect the brain's operational mechanisms, exploring the specific processes of memory storage and retrieval, understanding how neurons encode and reconstruct spatiotemporal experiences. These discoveries will explain why consciousness produces the illusion of faster-than-light travel. Though seemingly independent, these two research paths are intricately connected. Together, they converge upon a compelling conclusion. The speed of consciousness is not a true physical velocity, but rather a unique cognitive process. This process fully adheres to natural laws, whose manifestations are merely deceptively complex. In the following chapters, we shall traverse these two paths, delving into the laws of the cosmos and the mysteries of the brain. You will discover that when physics meets neuroscience, the enigma of superluminal consciousness unravels effortlessly. This journey of exploration itself resembles a wondrous cosmic voyage. Only our spacecraft is rational thought, and our navigator is the scientific method. Ultimately, at this intersection of disciplines, we shall gain new insights, understanding both the physical constraints of the universe and the unique essence of human consciousness. Now, let us embark on this dual scientific expedition. First, we enter the realm of Einstein's relativity, to explore the profound meaning of light speed as the ultimate cosmic velocity. In Newton's cosmic vision, time and space form an absolute, eternal backdrop. This classical worldview held that regardless of an observer's motion, the rate of time's passage and the measurement of spatial dimensions remain unchanged. Yet, as physicists delve deeper into electromagnetic phenomena, they discovered that the speed of light derived from Maxwell's equations is a constant. This constant appears entirely independent of an observer's own state of motion. This created a profound contradiction with the principle of velocity addition in classical mechanics. The young Einstein chose to confront this perplexing puzzle head-on. His 1905 theory of special relativity fundamentally reshaped our understanding of the universe. Special relativity rests upon two foundational principles. The first is the principle of relativity. It states that the laws of physics take identical form in all inertial reference frames. This means that within a closed cabin moving uniformly in a straight line, no physical experiment can determine whether you are in motion. The second principle is the constancy of the speed of light. It asserts that the speed of light in a vacuum remains constant in any inertial reference frame. Regardless of the relative motion between the light source and the observer, the speed of light always maintains a value of approximately 300,000 kilometers per second. These two fundamental principles, though seemingly simple, contain revolutionary conclusions. They first dismantled the traditional notion of absolute simultaneity. Suppose a light is turned on at the center of a train moving at constant speed. For an observer standing on the train, the light will reach both ends of the carriage simultaneously. However, for another observer standing on the ground, because the train is moving forward, the rear of the train is approaching the light wave while the front is receding from it. Therefore, this observer will see the light reach the rear before reaching the front. This thought experiment clearly demonstrates that simultaneity is not an absolute concept but depends on the observer's state of motion. When we extend this logic to time itself, we derive the time dilation effect. A classic example involves twin brothers, One embarks on a long journey in a spacecraft traveling near the speed of light, while the other remains on Earth. Upon the spacecraft's return to Earth, the astronaut brother will be significantly younger than his Earthbound sibling. This is not myth or fantasy, but a physically verifiable fact confirmed by experiments. In high-energy physics laboratories, the lifetimes of unstable particles are significantly prolonged during high-speed motion. This phenomenon aligns perfectly with relativistic predictions. Special relativity further reveals that space itself responds to motion. This is known as the length contraction effect. An object's length along its direction of motion shortens as its velocity increases. As speed approaches the speed of light, the length approaches zero. Notably, this contraction is not the result of mechanical compression, but rather the manifestation of spacetime's fundamental properties across different reference frames. The most renowned example is the mass-energy equivalence formula, which demonstrates that mass and energy are essentially two forms of the same entity. This profound insight not only explains the principle behind nuclear energy generation, but also unifies two of physics' most fundamental concepts. Special relativity weaves time and space into an inseparable spacetime fabric. Within this four-dimensional spacetime structure, each event is described by 3 spatial coordinates and 1 temporal coordinate. Different observers may disagree on their measurements of time and space, yet the spacetime intervals they measure remain consistently the same. This revolutionary theory reveals that the cosmic stage itself is elastic and dynamic, adjusting its form according to the motion of its actors. Einstein's genius lay in perceiving the essence behind appearances. The form of physical laws must remain consistent across all inertial reference frames, and the speed of light, as the ultimate limit for information transmission, must be an absolute constant. The combination of these two requirements naturally led to a new theory of spacetime. When we comprehend the cosmic landscape depicted by relativity, we realize that the speed of light limit is not an arbitrary rule, but an inevitable consequence of spacetime's intrinsic structure. Any attempt to breach this limit equates to altering the fundamental geometric properties of spacetime. This lays a solid foundation for our subsequent exploration of the relationship between consciousness and the speed of light. Within the framework of relativity, we must re-examine many intuitive concepts, including our conception of instantaneous information transmission. The constancy of the speed of light we will now explore further reveals the exquisite design of the cosmic structure. Throughout the long history of physics, no constant has occupied such a central position as the speed of light. Its value is approximately 299,792.458 meters per second. Behind this seemingly ordinary number lies one of the universe's deepest mysteries. From Galileo's first attempts to measure light speed to Roemer's estimation using Jupiter's moons, human understanding of the speed of light has evolved through a protracted process. Yet the true breakthrough came with Maxwell's electromagnetic theory. Through his system of equations, he deduced that the speed of electromagnetic waves is a fixed constant. This velocity precisely matched the measured values of light speed at the time. This discovery revealed light's essence as an electromagnetic wave. More significantly, the speed of light became a fundamental physical constant. It no longer depends on the motion of the light source or the observer. Michelson and Morley confirmed this property through precise interference experiments. Regardless of Earth's orbital motion, the measured speed of light remained constant. This result fundamentally shook the foundations of classical physics, paving the way for Einstein's revolutionary theory of relativity. The principle of the constancy of light speed is so crucial because it directly led to a fundamental transformation in the concept of spacetime. Within the relativistic framework, the speed of light becomes a geometric factor linking space and time. It defines the maximum rate at which causality can propagate. No form of energy transfer or signal transmission can surpass this ultimate velocity limit. We can grasp this through a thought experiment. Suppose we attempt to accelerate an object with mass. According to relativistic dynamics, the object's mass increases with velocity. As speed approaches the speed of light, mass becomes infinitely large. This would require infinite energy to continue acceleration. Therefore, any object possessing rest mass can only infinitely approach the speed of light, without ever reaching or exceeding this limit. For massless particles like photons, they inherently travel at the speed of light, but this also means they cannot exist at any other velocity. The speed of light acts like an insurmountable barrier set by the universe, strictly separating the possible from the impossible. The profound significance of this velocity limit also manifests in the preservation of causality. If information could propagate faster than light, it would lead to the inversion of cause and effect. An outcome might be observed before its cause occurred, completely undermining our fundamental understanding of event sequencing. Fortunately, the speed of light barrier prevents such paradoxes, ensuring the integrity of the causal chain. In modern physics, the role of light speed extends far beyond this. It appears in numerous fundamental physical equations, linking time with space, mass, and energy. Einstein's famous mass-energy equation serves as the prime example. This concise formula reveals the immense energy contained within matter, where the square of light speed acts as a colossal conversion factor, explaining the principles behind stellar luminosity and nuclear energy generation. On cosmological scales, astronomers employ light speed as a fundamental ruler. The unit light-year ingeniously bridges time and space. When we observe a galaxy 100 million light-years away, we are essentially witnessing the universe as it existed 100 million years ago. This unity of space-time rests precisely on the constant speed of light. Modern precision measurement techniques have fixed the value of light speed as a defined constant. The definition of the meter in the International System of Units directly depends on the speed of light. This definition embodies the benchmark status of light speed in physics. From quantum field theory to general relativity, from cosmic expansion to black hole physics, the speed of light remains an indispensable fundamental constant in these theories. Like an unchanging keynote in the cosmic symphony, all physical processes must adhere to this fundamental rhythm. When we gaze at the starry sky and see twinkling stars, each ray of starlight narrates the truth of the constant speed of light. These photons, traversing vast spacetime, journey through the cosmos at an eternal, unchanging velocity, bringing information from distant celestial bodies to our eyes. In this sense, the speed of light is not only the cornerstone of physics, but also the bridge connecting the universe to human cognition. Understanding the absoluteness of the speed of light is to grasp the fundamental laws governing the universe. This also establishes a solid scientific foundation for our subsequent exploration of the relationship between consciousness and the speed of light. In the realm of classical mechanics, an object's mass is regarded as a constant, unchanging intrinsic property. Newton's laws of motion imply that theoretically, with a sustained application of force, an object could accelerate indefinitely and reach arbitrarily high speeds. Yet when Einstein introduced the theory of special relativity, this seemingly self-evident notion was utterly overturned. Relativity revealed a startling truth. An object's mass is not constant, but increases as its velocity rises. This effect is negligible at everyday speeds, since we operate far below the speed of light. Yet, as an object's speed approaches light speed, the change in mass becomes profoundly significant. Mathematically describing this phenomenon requires introducing the crucial concept of the Lorentz factor. The relationship between the Lorentz factor and an object's velocity is intricate. When velocity is far below light speed, this factor approximates 1, making mass changes nearly negligible. However, as velocity gradually approaches the speed of light, the Lorentz factor begins to increase rapidly, causing the relativistic mass of the object to surge dramatically. Specifically, when velocity reaches 90% of the speed of light, the object's mass has already more than doubled compared to its rest mass. When velocity reaches 99% of the speed of light, the mass increases to 7 times the rest mass. As velocity approaches the speed of light, the Lorentz factor approaches infinity. This implies the object's mass also approaches infinity. According to the relativistic form of Newton's second law, acceleration equals force divided by mass. When mass approaches infinity, even the application of immense force will yield acceleration approaching zero. This creates an insurmountable barrier, where no finite force can accelerate an object to the speed of light. We can grasp this process through a vivid analogy. Imagine pushing a shopping cart. Initially, it feels light and accelerates easily, but as speed increases, it grows increasingly heavy, requiring ever greater force to continue accelerating. Near the speed of light, it becomes as heavy as the entire universe. Even expending all the energy in the cosmos couldn't move it an inch. This effect of mass expansion has been repeatedly verified experimentally. In particle accelerators at high-energy physics laboratories, electrons and protons can be accelerated to speeds extremely close to the speed of light. Experimental data precisely matches the predictions of relativity. When an electron moves at 99.99% of the speed of light, its mass exceeds 70 times its rest mass. These experimental results unequivocally confirm the validity of relativity. This limit can also be understood from an energy perspective. The kinetic energy formula takes on a new form within the relativistic framework. As velocity approaches the speed of light, kinetic energy no longer increases proportionally to the square of velocity, but grows at an accelerated rate. Accelerating a particle to the speed of light requires infinite energy, yet the total energy of the entire universe is finite. This energy requirement presents an insurmountable barrier. The principle of mass-energy equivalence also plays a crucial role here. Einstein's famous equation demonstrates that mass and energy are equivalent. When an object accelerates, its kinetic energy increases. This portion of energy also possesses mass. Thus, the total mass of a moving object comprises its rest mass and the mass corresponding to its kinetic energy. The higher the velocity, the greater the kinetic energy, and the larger the corresponding mass contribution. This creates a self-reinforcing cycle, rendering the speed of light an unattainable limit. For particles like photons, which possess zero rest mass, they must travel at the speed of light and cannot exist at any other velocity. This is a natural consequence of the relativistic wave equation. For objects possessing rest mass, they are forever confined to the subliminal realm. This cosmic law carries profound philosophical significance. It ensures the integrity of causality, prevents the inversion of temporal sequence, upholds the fundamental order of the universe. As we explore the relationship between consciousness and the speed of light, this physical constraint becomes a crucial reference point. Any discussion of superluminal travel must first confront this immutable natural law. The light year, a crucial unit of measurement in astronomy, is essentially a cosmic ruler woven from the speed of light. It is precisely defined as the distance light traverses in a vacuum over 1 Julian year. This distance equates to 9.46 trillion kilometers. When we use light years to describe the intervals between celestial bodies, we are, in essence, measuring space with time. This metric carries profound physical significance. In the boundless expanse of space, traditional geographical units lose all practical value. Even using standard length units like kilometers yields astronomically incomprehensible figures when describing interstellar distances. For instance, the distance from Earth to Proxima Centauri, our nearest star, would be expressed as a string of digits, 400 trillion kilometers. This number exceeds the bounds of human intuitive comprehension. Converting this distance to light years simplifies it to 4.24 light years. This expression is not only more concise, but immediately reveals crucial spatiotemporal information. What we observe is light emitted from Proxima Centauri 4.24 years ago. Each light-year figure narrates a chapter in the history of light's journey. Let us now turn our gaze to the deeper, more distant reaches of the cosmos. The diameter of our Milky Way galaxy is approximately 100,000 light-years. This means a beam of light emitted from one end of the galaxy would take 100,000 years to reach the other end. This simple figure gives us an intuitive sense of the galaxy's monumental scale. When we observe stars in the direction of the galactic center, what we see is actually their appearance tens of thousands of years ago. Such observations themselves amount to reviewing the history of the universe. Returning to the M78 nebula we mentioned earlier, it lies approximately 1,600 light-years from us. This figure tells us that the starlight we see now actually began its journey around the 5th century AD. When this beam of light left the nebula, Earth was in the era of the Roman Empire's decline. By the time it traversed interstellar space to reach Earth, human civilization had undergone 1,000 years of transformation. On an even grander cosmic scale, the Andromeda galaxy we observe radiates the brilliance of 2.5 million years ago. The most distant galaxies captured by the Hubble telescope have been traveling through the cosmos for over 10 billion years. These observational facts transform astronomical telescopes from mere instruments for observing space into time machines exploring the mysteries of time. The concept of the light year is so crucial because it is founded on the constant speed of light. It is precisely the absolute constancy of light speed. Can we confidently employ it as the cosmic ruler? If light speed varied over time or with an observer's motion, the entire astronomical distance system would lose its foundation. Many discoveries in modern cosmology rely on the precision of light years. From stellar parallax measurements to the period-luminosity relationship of Cepheid variables, from type Ia supernova distance measurements to redshift observations, these methods ultimately translate into distances measured in light-years or seconds of light. These distance measurements reveal that the universe is expanding. Galaxies are moving apart, and the rate of expansion is accelerating. The light-year is not merely a spatial unit. It is a crucial tool for exploring cosmic evolution. When we speak of the observable universe's radius of approximately 46.5 billion light-years, this figure reflects both the universe's 13.8 billion year age and the combined effect of cosmic expansion. This seemingly contradictory number precisely embodies the elegance of modern cosmology. Now let us return to the theme of consciousness and the speed of light. When your consciousness instantly reaches the M78 nebula, you have actually traversed 1,600 light-years of spacetime. This experience stands in stark contrast to the speed of light limit. Understanding the true meaning of the light year as a physical distance reveals that so-called superluminal travel by consciousness is merely an intricate cognitive illusion. In the following discussion, we will delve into the neural mechanisms behind this illusion. Observe how the brain crafts such awe-inspiring space-time traversal experiences. without violating physical laws. This light-year ruler measures both the universe's vastness and illuminates the extraordinary capabilities of human consciousness. As humanity's most familiar yet enigmatic phenomenon, has been the central subject of philosophical and scientific inquiry since antiquity. From Plato's world of forms to Descartes' dualism, philosophers have debated the nature and origin of consciousness. Descartes' famous proposition, "I think, therefore I am," established consciousness as an unshakable foundation of cognition. Yet he simultaneously fell into the trap of mind-body dualism, unable to explain how intangible consciousness interacts with the tangible body. Modern scientific advancements have offered new perspectives. Consciousness is no longer viewed as a sole entity separate from matter, but rather as a product of the highly complex material entity known as the brain. This perspective is termed physicalism or naturalism. A challenging explanatory gap persists in contemporary consciousness research. This term was first explicitly coined by philosopher Levine. It refers to how physical processes in the brain generate subjective experience. This seemingly simple question continues to perplex scientists. We can perfectly describe the biochemical mechanisms of neuronal firing, yet cannot explain why these electrochemical activities are accompanied by a warm sensation, nor why specific neural patterns produce the experience of red. This gap lies between objective description and subjective experience, forming the most fundamental challenge in consciousness research. The renowned philosopher of mind, Chalmers, distinguishes two categories of consciousness problems: the easy question and the hard question. The easy question concerns the mechanisms of cognitive functions, such as the neural foundations of attention, memory, and thought processes. Though complex, these can in principle be addressed through scientific methods. The hard problem, however, concerns why these processes are accompanied by subjective experience. Why doesn't all information processing occur silently in the dark? This distinction helps clarify the hierarchy of consciousness research. Within neuroscience, researchers explore consciousness through multiple approaches. Functional magnetic resonance imaging, fMRI, reveals brain region activation during conscious activity. Electroencephalography, EEG, captures electrical signal changes associated with conscious states. Studies of brain-damaged patients reveal the relationship between specific brain regions and consciousness. These investigations all point to one conclusion: consciousness is inextricably linked to the brain's physical state. The global workspace theory was proposed by cognitive scientist V.S. Bales. This theory posits that consciousness corresponds to the propagation of information across the brain's global workspace. When a piece of information becomes conscious, it is broadcast to various specialized systems throughout the brain. This theory has been supported by a series of experimental evidences. Another significant theory is the information integration theory, developed by neuroscientist Tononi and colleagues. This theory attempts to mathematically quantify levels of consciousness, arguing that consciousness corresponds to a system's capacity for integrating information. Though differing in perspective, these theories all seek to explain consciousness within a scientific framework. From an evolutionary biology perspective, consciousness may represent an adaptive mechanism emerging under natural selection pressures, enabling organisms to integrate diverse information and make more flexible decisions. This ability confers a survival advantage in complex, changing environments. However, the evolutionary explanation still cannot fully answer the hard problem. Why must this information integration be accompanied by subjective experience? In this discussion, we adopt a scientific stance and define consciousness as a product of neural activity in the brain. It encompasses both the holistic perception during wakefulness and the subjective experience of specific content. When we speak of consciousness traveling back in time or reaching nebulae, we are discussing specific functional states of the brain, rather than some mystical force transcending physical laws. While this definition does not resolve all philosophical puzzles, it provides a solid foundation for our subsequent scientific inquiry. It will help us understand the neural mechanisms of conscious experience, and why these mechanisms produce the illusion of faster-than-light phenomena, while fully adhering to the physical laws of the universe. Within this framework, consciousness ceases to be an elusive phantom, but becomes the luminous operation of the brain, a complex biological machine. We need neither mystify nor oversimplify it, but should instead explore its mysteries through scientific methods, just as we use science to explore the mysteries of the universe. The essence of consciousness and the essence of the universe may ultimately point to the same natural truth. The human brain can be regarded as an internal universe, whose complexity rivals the starry sky above our heads. This organ, weighing merely about 1.4 kilograms, contains a staggering 86 billion neurons, a number nearly equivalent to the stars in our Milky Way galaxy. Each neuron resembles a miniature star, forming a vast neural network through intricate connections. When we delve into the microscopic structure of the brain, we discover the intricate organization of this inner universe. Neurons connect through synapses, forming neural fibers whose total length can reach hundreds of thousands of kilometers. The total number of these connections reaches the trillions, a figure surpassing even the number of stars in our Milky Way galaxy. The brain's white matter resembles dark matter in the cosmos. Though not directly involved in information processing, it provides the infrastructure for neural signal transmission. The neuron cell bodies within gray matter shine like luminous stars, glowing with electrochemical light at the microscopic level. When unfolded, the cerebral cortex spans approximately 0.2 square meters. This seemingly modest surface is densely covered with gyri, resembling the filamentary structures of galaxy distribution in the universe. These folds dramatically increase the cortex's surface area, allowing us to pack more computational units within our finite cranial cavity. Different brain regions function like distinct celestial systems in the cosmos, each performing specialized roles while working in close coordination. The prefrontal cortex acts as a command center, overseeing higher cognitive functions and decision-making. The visual cortex functions as a sophisticated signal-receiving station, processing visual information from the eyes. The hippocampus acts as a memory transit station, overseeing the conversion of short-term memories into long-term storage. The cerebellum functions as a sophisticated motion coordinator, ensuring the fluid execution of every movement. These regions are interconnected by bundles of nerve fibers, much like the cosmic web linking galaxies in the universe, forming a complex and highly efficient information highway. The manner of information transmission between neurons is astonishing. Electrical signals travel along axons at speeds ranging from 1 to 100 meters per second. Though far below the speed of light, this velocity is remarkable at the microscopic scale. When signals reach synapses, even more wondrous processes unfold. Neurotransmitters act as interstellar messengers, crossing synaptic gaps just 20 to 40 nanometers wide, to deliver information to the next neuron. This process mirrors cosmic civilizations, transmitting knowledge through electromagnetic waves between stars. The brain's plasticity is the most miraculous trait of this inner universe. Neural connections are not static, but constantly reshape themselves through experience and learning. New synaptic connections continually form, while unused connections gradually weaken. This process mirrors the evolution of galaxies in the cosmos. Where stars are born and die, Galaxies merge or separate, forever in dynamic flux. The brain's energy consumption is also astonishing. Though it accounts for only 2% of body weight, it consumes 20% of the body's oxygen and energy. This energy consumption ratio is unique in nature, much like certain active galactic nuclei, releasing astonishing energy within a confined space. The brain's developmental process itself is a cosmic evolution story. Beginning in the embryonic stage, neurons are generated at a rate of 250,000 per minute, migrating along scaffolds built by glial cells, gradually forming complex hierarchical structures. This process mirrors the formation of early galaxies in the cosmos. Primordial matter aggregates and evolves under gravitational forces. When comparing the brain to the universe, we discover astonishing parallels. The cosmos contains dark matter and dark energy. The brain harbors silent synapses and resting states. The universe holds black holes and stellar explosions. The brain experiences all-or-nothing neuronal firing. The cosmos emits gravitational waves and electromagnetic radiation. The brain possesses electric field oscillations and chemical diffusion. These parallels transcend superficial analogies to reveal deep, shared principles of complex systems. Within this internal cosmos, consciousness functions like light in the universe, both a product of the system's operation and the tool through which we observe it. When we contemplate the brain's complexity, we are, in essence, thinking about the brain itself. This self-referential nature makes brain research exceptionally fascinating and exceptionally challenging. Understanding the structure of this inner universe called the brain provides the essential knowledge foundation for our subsequent exploration of the neural mechanisms of consciousness. Just as astronomers must first understand the structure of galaxies, to comprehend stellar evolution, we must first grasp the brain's architecture. To understand consciousness, the most mysterious phenomenon. In this journey of exploration, we discover that the most distant universe and the closest brain actually follow similar natural laws. The transmission of neural signals is fundamentally a precise physicochemical process. It follows deterministic natural laws requiring no supernatural explanation. This process begins with the electrochemical gradient across the neuronal cell membrane. At rest, neurons maintain a membrane potential of -70 millivolts. This potential relies on the continuous operation of the sodium-potassium pump. For every ATP molecule consumed by this protein, 3 sodium ions are pumped out of the cell while 2 potassium ions are pumped in. This asymmetric exchange creates a concentration gradient of ions across the cell membrane. Much like a battery storing electrical potential energy through chemical reactions, when a neuron receives a sufficiently strong stimulus, voltage-gated sodium channels undergo a conformational change. These minute protein channels open within millionths of a second, allowing positively charged sodium ions to flood into the cell along the concentration gradient. This process triggers rapid depolarization of the membrane potential. When the membrane potential reaches a threshold of approximately -55 millivolts, it triggers an all-or-nothing action potential. The generation of action potentials follows strict physical laws. Ion flow strictly adheres to electrochemical gradients. No mysterious forces intervene. Action potentials propagate along axons at a constant amplitude. Their speed depends on axon diameter and myelin coverage. In myelinated fibers, signals conduct by saltatory conduction between Ranvier nodes. This method can boost transmission speeds up to 100 meters per second. Nevertheless, this remains far below the speed of light. When the electrical signal reaches the axon terminal, it triggers calcium ions to flow inward through voltage-gated channels. Vesicles within the presynaptic membrane fuse with the cell membrane, releasing stored neurotransmitters into the synaptic cleft. This process resembles a meticulously choreographed molecular dance. Each step is governed by physical and chemical laws. Neurotransmitter molecules diffuse through Brownian motion across the synaptic cleft, which is only 20 to 40 nanometers wide. Though seemingly random, this diffusion process fully complies with the principles of statistical physics. At the postsynaptic membrane, neurotransmitters bind to specific receptors. These receptors themselves are molecular machines composed of proteins. Their conformational changes activate ion channels, resulting in the influx or efflux of specific ions into or out of the postsynaptic neuron. Depending on the channel type, this may generate excitatory or inhibitory postsynaptic potentials. These minute potential changes are integrated temporally and spatially to determine whether downstream neurons will fire new action potentials. The fate of neurotransmitters released into the synaptic cleft is predetermined. They may be enzymatically degraded or reabsorbed for recycling. This highly efficient reuptake mechanism ensures precise control of neural signaling. The entire process resembles a precision industrial production line, with each step meticulously regulated at the molecular level. From action potential generation to neurotransmitter release, from receptor binding to signal termination, each step constitutes a purely physicochemical reaction. The energy expended in these processes ultimately originates from the oxidation of glucose. Through cellular respiration, ATP molecules are generated to power sodium-potassium pumps and other molecular machines. This energy conversion process likewise adheres to thermodynamic laws. No step violates known physical principles. When we contemplate a simple thought, millions of neurons in the brain participate in this precise physicochemical process. Their coordinated activity generates specific discharge patterns. Though intricate, these patterns are entirely explainable by physical-chemical principles. The neural foundation of consciousness is built upon these physical processes. No evidence suggests the need for supernatural explanations. While neural signal transmission has inherent limitations, the brain compensates through parallel processing. Billions of neurons working simultaneously create astonishing cognitive capabilities. Yet no matter how complex this system becomes, it always operates within a deterministic physical framework. Understanding the physical nature of neural signals is crucial for exploring the relationship between consciousness and the speed of light. It reveals that any manifestation of consciousness must adhere to fundamental physical laws, including the cosmic principle that the speed of light is an unbreakable barrier. With this understanding, we can grasp why the instantaneous nature of consciousness is merely an ingenious illusion, rather than a genuine superluminal phenomenon. When billions of neurons synchronously discharge in specific patterns, a wondrous emergent phenomenon arises within the brain. The essence of this emergence is that the whole is greater than the sum of its parts. Much like countless water molecules coalescing into a mighty river, a single neuron can only transmit simple electrical signals. But when they form complex networks, consciousness magically emerges from the network. This transition from quantitative to qualitative change is not supernatural, but a universal natural law of complex systems. Just as each ant in a colony exhibits simple behavior, yet the entire colony displays astonishing intelligence. Consciousness is an emergent property of the brain's complex system. The global workspace theory provides a compelling explanation. When information is processed by a specialized system in the brain, it may remain at the unconscious level. Once this information competes its way into the global workspace, it is broadcast throughout the entire brain. At this point, conscious experience arises. This theory elegantly explains why we can only be aware of a limited amount of content at any given time. Because the global workspace is like a spotlight on a stage. It can only illuminate a few actors at a time. The integrated information theory explores consciousness from a mathematical perspective. This theory posits that consciousness corresponds to a system's ability to integrate information. When a system is both highly specialized and highly integrated, consciousness naturally emerges. This theory quantifies consciousness levels using the Greek letter phi. Though the specific calculations are extremely complex, the fundamental idea is profoundly insightful. The brain structure is particularly suited for high-level information integration. Different brain regions are both functionally specialized and interconnected, much like musicians in a symphony orchestra, who can play their own parts while coordinating with each other, ultimately giving rise to a harmonious symphony. The emergence of consciousness has several key characteristics. First is wholeness. Conscious experience constitutes a complete whole. We cannot simultaneously experience two independent consciousnesses, just as we cannot listen to two different symphonies at once. Second is information richness. Each conscious state contains vast amounts of information. When you see the color red, this experience encompasses countless details like hue, shape, and texture. These details integrate instantaneously into a unified experience. Third is proactivity. Consciousness does not passively reflect the world. It actively constructs it, based on incoming signals and prior knowledge, to continually construct our experience of the world. This construction process itself is an emergent phenomenon. From an evolutionary perspective, the emergence of consciousness is not accidental. It likely provided organisms with a survival advantage. Conscious beings can adapt more flexibly to their environment and engage in more complex planning and decision-making. However, this advantage does not require consciousness to transcend physical laws. The emergence of consciousness fully follows natural laws. It does not require an additional soul or mystical force. It only requires sufficiently complex neural networks and appropriately organized structures. Modern computer science has witnessed similar phenomena, where simple rules generate unexpected behaviors in complex systems. This further confirms emergence as a universal principle in nature. When we say consciousness emerges from the brain, we are not diminishing its value. Rather, we are scientifically understanding its origins. Just as understanding life emerging from molecules does not diminish life's miraculous nature, understanding the emergent nature of consciousness is crucial for exploring consciousness's relationship with the speed of light. It reveals that any manifestation of consciousness, including its apparent ability to traverse time and space instantaneously, is the result of this complex system operating within the framework of physical laws. There is no evidence suggesting consciousness requires breaking the speed of light barrier. With this understanding as our foundation, we can delve deeper into why consciousness generates the illusion of superluminal speed. This illusion itself may be yet another manifestation of consciousness's emergent nature. The speed at which neural impulses travel within the brain has a clear physical upper limit. This speed limit is determined by fundamental principles of neurobiology. Different types of neurons possess distinct signal conduction speeds. The thinnest unmyelinated nerve fibers conduct signals most slowly. Their speed ranges from just 0.5 to 2 meters per second. This is slower than a person walking at a leisurely pace. Slightly thicker myelinated nerve fibers exhibit significantly faster speeds, reaching 10 to 30 meters per second, roughly equivalent to the cruising speed of urban vehicles. The largest myelinated nerve fibers in the human body perform best. achieving peak speeds of 120 meters per second, a figure approaching the speed of sound in air. Yet even the fastest neural signals only reach 1/400,000th of the speed of light. Let's make an intuitive numerical comparison. Light travels approximately 300,000 kilometers per second in a vacuum. This distance is equivalent to circling the Earth 7.5 times. Meanwhile, the fastest neural signal can only advance 120 meters per second. This distance is less than one lap around a standard athletics track. When a bolt of lightning flashes across the sky 10 kilometers away, the light reaches your eyes in 1/30,000th of a second. However, the neural signal conveying this visual information requires nearly 1/10th of a second to complete processing in the brain's visual cortex. Though fleeting, this time difference speaks volumes. During the period of slow neural signal transmission, light could travel between Earth and the Moon over 6 times. This disparity in speed represents an order of magnitude fundamental difference. The physical limitations on neuronal conduction speed stem primarily from several factors. The resistive properties of axons slow electrical signal propagation. The capacitive effect of cell membranes further delays signal transmission. The insulating properties of myelin sheaths directly impact the efficiency of saltatory conduction. These factors collectively determine the maximum speed of neural impulses. From an energy expenditure perspective, this represents an optimized outcome. Faster conduction would require thicker axons and greater energy investment. During evolution, the brain found a balance point, making the optimal trade-off between speed and energy consumption. Modern neuroscience measures these speeds through multiple methods. Microelectrode recordings directly detect electrical signal propagation along axons. Electroencephalography measures the synchrony of large-scale neural activity. Magnetic resonance imaging indirectly displays signal transmission between brain regions. All these measurements point to the same conclusion. No neural signal can breach this physical limit. When we speak of consciousness seemingly reaching distant nebulae in an instant, we must understand the actual neural processes behind it. Your brain isn't sending signals to the M78 nebula, but rather activating internal memory representations of that nebula. This activation process strictly adheres to the speed constraints of neural transmission. Though it feels instantaneous, it actually requires tens to hundreds of milliseconds. This duration is sufficiently rapid for the brain's perceptual systems to create the illusion of instant completion. Understanding the true speed of neural impulses is crucial for correctly understanding conscious phenomena. It clearly demonstrates that no matter how wondrous conscious experiences may seem, they remain bound by fundamental physical laws. Within this cognitive framework, we can better comprehend why the faster-than-light experience of consciousness is merely an illusion, and this illusion itself is precisely a manifestation of the brain's highly efficient information processing capabilities. When you recall a summer afternoon from your childhood, you are not truly traveling back in time to that moment. Your brain is executing a sophisticated simulation. This process begins with the retrieval of memories. The hippocampus, acting as the brain's indexing system, is first activated to search for relevant memory traces. These traces are not complete video recordings, but fragmented information stored across different brain regions. The visual cortex preserves the scene's imagery from that time. The auditory cortex records the cicada's constant chirping. The olfactory cortex seals the scent of grass and earth. The somatosensory cortex retains the warmth of sunlight on skin. The prefrontal cortex tags the experience with temporal and emotional labels. These scattered memory fragments are simultaneously activated, like musicians in a symphony orchestra, each playing their distinct part. The prefrontal cortex acts as the conductor, integrating these scattered melodies into a harmonious composition. The process of memory reconstruction is creative and uncertain. The brain does not simply replay past recordings. Instead, it reconstructs a plausible scenario simulation based on residual memory traces in the present. This process resembles an archaeologist reconstructing ancient artifacts from fragments, requiring reasonable filling in based on existing knowledge. When recalling a birthday party from years ago, the brain may borrow details from other similar scenarios, or even incorporate entirely fictional elements. This reconstructive mechanism explains why memories change over time. Each recollection is a new construction process that modifies the original memory to some degree. Neural-level mechanisms similarly support this theory. When a memory is retrieved, the corresponding neural circuitry reactivates. This activation alters the strength of synaptic connections, potentially yielding different versions upon subsequent retrieval. From an information processing perspective, this represents an efficient design. The brain need not store complete scene data, requiring only key features and relationships. These features are then utilized to regenerate scenes when needed, significantly conserving neural storage space. The trade-off, however, is memory accuracy and stability. Comparing real perception with memory reconstruction reveals both employ similar brain mechanisms. Functional magnetic resonance imaging studies show high overlap in brain regions activated during visual perception and visual imagery. The primary distinction lies in the direction of information flow. During perception, information travels from sensory organs to higher cortical areas. During imagery, information feeds back from the prefrontal cortex to sensory cortex. This discovery of a shared mechanism holds significant implications. It suggests that what we call returning to the past actually involves creating a simulation of the past in the present. This simulation, based on residual memory data, is processed by the brain to produce a realistic effect. The emotional dimension of memory is similarly reconstructed. When recalling a sad event, interaction between the amygdala and prefrontal cortex regenerates similar emotions. Yet this emotion is a newly generated response in the present, not the original feeling preserved from the past. This mechanism protects us from persistent immersion in past emotions, while explaining why emotional memories are more easily modified. Temporal markers pose a unique challenge in memory reconstruction. The brain lacks a dedicated organ for recording time. Temporal information is inferred through multiple cues, including the age of the memory, the sequence of events, and associations with other known temporal events. When we judge a memory to have occurred 10 years ago, we are actually performing complex temporal reasoning, rather than reading a precise timestamp. This reconstruction theory perfectly explains the illusion of time travel in consciousness. When you feel transported back to the M78 nebula 1600 light-years away, your brain is merely activating present-day knowledge about that nebula, including its visual characteristics, astronomical data, and your initial emotional response upon first encountering it. All this information resides within your brain, requiring neither superluminal signal transmission nor time travel violating physical laws. Every step of this process strictly adheres to neurobiological principles, operating within finite speed constraints. Understanding the reconstructive nature of memory reveals that consciousness's ability to traverse time and space is a cognitive illusion. Yet this illusion reveals the brain's extraordinary creativity, allowing us to safely experience scenarios across different times and spaces. Perhaps this is evolution's precious gift to humanity, enabling us to learn from the past and plan for the future without bearing the physical costs of actual time travel. The passage of time we perceive is not an exact clock recording, but a subjective experience constructed by the brain through complex processing. This subjective time exhibits remarkable elasticity, capable of compressing or extending actual physical time intervals. When you complete a rapid eye movement, the physical process takes hundreds of milliseconds to complete, yet you perceive the world as continuous and instantaneous. This illusion stems from the brain's post-processing editing mechanism. External information requires varying processing times to reach the brain. Visual signals take 50 to 100 milliseconds to reach the visual cortex. Auditory signals require only 10 to 15 milliseconds for processing. Tactile signals demand 20 to 50 milliseconds of conduction time. These temporal discrepancies should inherently cause perceptual asynchrony. Yet the brain ingeniously integrates them through a temporal binding window. This mechanism aligns information from different senses onto a unified timeline, typically lasting 1 to 200 milliseconds. All signals arriving within this window are perceived as occurring simultaneously. This mechanism ensures the coherence of our world perception. Yet it simultaneously distorts the true temporal relationships. The brain also possesses a unique ability to predict the future. It can anticipate upcoming events based on past experiences, and consciously project this prediction ahead of time. When you catch a thrown ball, what you perceive is a real-time event, but in reality, the brain has already calculated the ball's trajectory and projected this prediction onto the present moment. This feed-forward mechanism significantly shortens reaction time, but also further distorts our perception of time. The process of accessing memories also influences time perception. When recalling an event, the brain does not replay it according to its original duration. Instead, it compresses the memory based on the event's information density. A journey filled with novel experiences seems to pass in an instant, while monotonous waiting feels interminably long. This discrepancy stems from differences in memory storage. High-information events occupy more memory resources. Recalling these rich details requires longer retrieval time, creating the subjective illusion of time dilation. Attention allocation profoundly reshapes temporal experience. When fully immersed in an activity, time seems to fly by, yet during tedious waiting periods, each moment stretches endlessly. This phenomenon stems from the brain's processing of temporal information. During intense focus, time monitoring mechanisms are suppressed. In boredom states, these mechanisms become hyperactive. Neuronal oscillation theory explains this mechanism. Different frequency oscillations within the brain may function as internal clocks. When attention shifts, the frequencies of these oscillations change, leading to subjective acceleration or deceleration of time perception. Emotional states exert an even more pronounced influence on time perception. In dangerous situations, time seems to slow down. This experience may stem from activation of the amygdala, which intensifies memory encoding strength and parallel processing capabilities, significantly increasing the information stored per unit time. During recall, this dense information requires extended psychological time for processing, thereby creating an illusion of temporal prolongation. When contemplating distant celestial bodies, consciousness appears capable of instantaneous space-time traversal. This sense of immediacy embodies the elasticity of subjective time. When the brain retrieves memories of the M78 nebula, it actually undergoes multiple stages of neural processing, from hippocampal memory indexing to visual cortex image reconstruction, from prefrontal scene integration to emotional system resonance. This process requires hundreds of milliseconds of actual time. Yet because most of these operations occur in parallel, and the final presentation is a fully integrated scene, we perceive no temporal delay. This effect resembles watching a movie. though composed of discrete frame sequences. We perceive fluid, continuous motion. The brain integrates discrete neural signals into coherent narratives, granting us a seamless, subjective experience of time. Understanding the elastic nature of subjective time is crucial. It reveals the essence of conscious experience. The reality we perceive is not a direct mapping of the objective world, but a carefully constructed product of the brain's processing. The sensation of instantaneous time traversal is a masterpiece of this construction. It requires no violation of physical laws, only the full utilization of the brain's information processing characteristics. Within this cognitive framework, we can both appreciate the marvels of consciousness and maintain a fundamentally scientific and rational stance, recognizing that while conscious experience transcends physical time, its underlying mechanisms fully comply with natural laws, enables us to better grasp humanity's unique position in the cosmos, both as integral components of the physical world and as beings capable of transcending physical constraints through consciousness, experiencing infinite possibilities on a subjective level. The chain of causality forms the fundamental operating logic of our universe. This logic rests upon the irreversibility of the arrow of time. The second law of thermodynamics reveals time's true direction. The entropy of an isolated system invariably increases. This profound physical principle acts like the universe's clockwork, ensuring events always progress from order to disorder, flowing from past to future. A drop of ink in clear water will naturally disperse, yet never spontaneously reassemble into its original droplet. A shattered glass bottle will not automatically restore itself to its original state. Behind these everyday phenomena lies the principle of entropy increase. Entropy as a measure of a system's disorder. Its singular increase endows time with a definite direction. At the microscopic level, particle motion follows statistical laws, though the motion of individual molecules is reversible. Systems composed of vast numbers exhibit statistical irreversibility. This contradiction between microscopic reversibility and macroscopic irreversibility lies at the heart of statistical physics. Tracing the origins of the universe reveals that time's arrow began with the Big Bang. The primordial cosmos existed in a state of extreme order and high energy. As the universe expanded and cooled, the distribution of matter gradually became disordered and dispersed. This universe-scale process of entropy increase sets the tone for all local arrows of time. Within the framework of general relativity, the space-time structure itself adheres to strict causality. The light cone of any event defines its causal boundary. The past light cone contains all possible causes that could influence that event, while the future light cone encompasses all possible outcomes that the event might affect. These two cones are separated by an impassable present. The speed of light limit ensures causality cannot be reversed. In the realm of quantum mechanics, though the causality of individual events becomes blurred, statistical causality remains valid. Quantum entanglement appears to permit superluminal correlations, yet it cannot be used to transmit meaningful information. Thus, it cannot undermine the integrity of causality. From a neuroscience perspective, our brain's operations likewise adhere to causality. Every thought's emergence, every decision's formation, is the result of preceding neural activity, while simultaneously becoming the cause of subsequent neural activity. This causal chain continuously extends within the brain, forming the foundation of our thought and consciousness. When discussing consciousness returning to the past, we must distinguish between actual causality and subjective experience. The act of recollection does indeed evoke past memories. However, this does not imply we alter the causal chain of the past. The brain merely reconstructs scenarios based on past experiences in the present moment. This reconstruction process itself still adheres to the law of causality. The current mental state is the cause. The content of the recollection is the effect. This causal relationship still progresses along the arrow of time. If consciousness could truly travel backward through time, it would imply effects occurring before their causes. This would lead to a logical infinite paradox. The famous grandfather paradox exemplifies this flaw. If you travel back to kill your grandfather, you would never be born. Since you would never be born, how could you possibly travel back to commit the act? Such logical contradictions remain unsolvable within the framework of physics. Thus, preserving the integrity of causality is fundamental to the orderly functioning of the universe. Modern physics continually validates this principle. From black hole thermodynamics to quantum field theory, from cosmic inflation theory to dark energy research, all theories must ensure the law of causality remains intact. This principle has become the cornerstone for constructing physical theories. When exploring the relationship between consciousness and the speed of light, the law of causality provides the most crucial criterion for evaluation. Any activity of consciousness must obey the law of causality, just as it must obey the speed of light limit. When we feel consciousness instantly returning to the past, it is actually the present processing and manipulating memories. This processing follows the normal causal sequence. First, the neural signals for memory retrieval occur. Then, the formation of conscious experience follows. The entire process unfolds along the normal direction of time. Understanding the iron law of causality helps us recognize the true nature of consciousness. It is neither a supernatural entity, nor an exception to physical laws. Rather, it is the normal function of the brain, a complex physical system. Within this cognitive framework, we can appreciate the wonder of consciousness. Without falling into the pitfalls of mysticism, the universe maintains its order through the law of causality. As a product of the universe, consciousness naturally adheres to this fundamental principle. This is why, no matter how free consciousness may feel, can never truly defy the arrow of time, cannot alter the past that has already occurred. This understanding fosters a profound reverence for the universe, for time, and for ourselves. Memory is the brain's internal reconstruction of past experiences. History is the objective sequence of events unfolding in space-time. This fundamental distinction mirrors the relationship between a map and the territory. Memory is the subjective map we draw. History is the objective territory it seeks to describe. The two may resemble each other but can never be identical. Memory formation begins with the initial encoding of sensory information. The very process of converting external stimuli into neural signals is inherently selective. We can only register partial information from our environment. Only this noticed information enters the memory system. The subsequent consolidation phase involves more processing. The hippocampus and cortex work together to transform short-term memories into long-term ones. During this process, information is simplified and reorganized. Memory storage is not a complete video recording, but rather fragments of features distributed across different brain regions. Visual elements are stored in the occipital lobe. Auditory information resides in the temporal lobe. Spatial relationships are stored in the parietal lobe. Emotional tags reside in the hippocampus and amygdala. When we recall memories, the brain undertakes a reconstruction project. Based on stored fragmentary information, it reconstructs a plausible scene in the present moment. This process resembles an archaeologist reconstructing an ancient vase from shards, inevitably involving speculation and filling in gaps. Memory reconstruction is influenced by multiple factors: Current emotional states color memories. Sadness often makes recollections appear darker. Knowledge background alters how memories are interpreted. Recalling childhood events as an adult yields entirely different understandings. Subsequent experiences continually overwrite original memories. Each recollection is a process of rewriting history as an objective sequence of events. Its authenticity does not depend on any observer. In 44 BC, Caesar was assassinated in the Senate. This event exists independently of anyone's memory or description of it. Its occurrence is defined by changes in the state of matter within the universe. History follows a strict chain of causality. Each event is the inevitable outcome of preceding events under physical laws. This objectivity rests upon the determinism of the material world. Neuroscience experiments reveal the unreliability of memory. Loftus's research demonstrates that false information can be implanted into memory. Leading questions can prompt people to recall events that never happened. The brain even creates vivid details for these fabricated events. Functional magnetic resonance imaging shows that brain regions activated by true memories and false memories highly overlap. Even the individuals themselves cannot reliably distinguish between the two. The distortion of collective memory is even more pronounced. Historical events are continually reconstructed during group transmission. Details are simplified, emotions amplified, narratives standardized. The collective memory that ultimately forms may diverge significantly from the original event. Meanwhile, historical truth lies quietly within the coordinates of time and space. It remains unchanged by anyone's memory or description. From a philosophical perspective, this distinction becomes even more profound. Memory belongs to the realm of epistemology. It concerns how we perceive and understand the world. History belongs to the realm of ontology. It concerns the very state of existence of the world itself. We forever observe history through the filter of memory. Yet this does not alter history's inherent objectivity. The distinction between memory and history proves particularly critical within the judicial system. A witness's testimony in court is fundamentally a report of memory, whereas the truth of a case is the objectively occurring history. The potential gap between the two determines the fairness of judicial rulings. This is precisely why physical evidence is required to corroborate testimony. For physical evidence constitutes the material traces left by historical events. Understanding this distinction on a personal level holds therapeutic value. When we suffer from past experiences, we are actually wrestling with our memories of the events, not with the events themselves. Memories can be reinterpreted and reintegrated, thereby altering their impact upon us. Historical events, however, are forever fixed at a specific point in spacetime. From a physics perspective, history is composed of all event points within spacetime. Each event possesses definite spacetime coordinates. Their intervals are Lorentz invariant. This means history is objectively absolute, unchanged by the observer's reference frame. Memory, however, exists as a neural state within the brain. Its accuracy is strictly constrained by biology. This limitation is not a flaw but a defining characteristic. To function efficiently, the brain must compress information, retaining only data critical for survival and reproduction. Complete recording would consume excessive energy, a trait not selected for during evolution. Modern information theory offers a fresh perspective on this distinction. Memory is a packet of information subjected to lossy compression. History, however, is uncompressed raw data. We cannot fully restore the original data from a compressed file, just as we cannot recover every original pixel from a JPEG image. Understanding the difference between memory and history is crucial for exploring the relationship between consciousness and time. When we feel consciousness returning to the past, we are actually accessing current memory representations, rather than truly returning to that specific point in spacetime. Memory's vividness creates the illusion of traversal, yet physical laws ensure we remain anchored in the present. This awareness allows us to enjoy memory's richness, while maintaining respect for historical truth. In our pursuit of scientific truth, we must constantly guard against memory's subjectivity, while firmly believing in history's objectivity. This balanced approach embodies the essence of rational thought. Within the strict framework of Einstein's special relativity, no material entity or energy transfer can exceed the speed of light in a vacuum. This universal constant establishes the ultimate limit for the propagation of causality, ensuring the definitive boundary between past and future remains impassable. Yet human consciousness exhibits a unique capacity for temporal regression. This ability appears to conflict with relativity's fundamental principles. However, upon examining the nature and mechanisms of consciousness, we discover that this temporal regression is purely a subjective phenomenon. Consciousness's access to the past is fundamentally an internal information processing mechanism. It involves neither the superluminal displacement of matter or energy through space, nor the retroactive transmission of information into past time. When recalling memories, the brain activates pre-existing neural connection patterns. These patterns encode the memory traces left by past experiences. The formation of memory traces stems from historical events shaping neural networks. Each memory trace corresponds to a physical event at specific spatiotemporal coordinates. Yet the memory trace itself resides within the present brain structure. When we recall the past, we are actually reactivating these neural patterns in the present moment. This process strictly follows normal causal temporal sequences. From a neurobiological perspective, memory retrieval is a standard neural signal transmission process. Electrical signals propagate through axons at finite speeds. Chemical signals diffuse across synaptic gaps according to established patterns. The entire process consumes time ranging from tens to hundreds of milliseconds. Although this speed is far below the speed of light, due to the brain's highly parallel information processing and the post-integration nature of conscious experience, we experience the illusion of instantaneously returning to the past. Functional magnetic resonance imaging studies provide compelling evidence for this. When subjects recall past events, the brain activates the default mode network responsible for scene reconstruction, rather than any anomalous state that might violate relativity. The neural basis of memory fully adheres to physical laws. Special relativity prohibits physical time travel, that is, the movement of physical entities along world lines to past spacetime coordinates. Such travel would cause severe causal paradoxes. The famous grandfather paradox exemplifies this most clearly. If someone travels back to kill their grandfather, their own existence becomes logically impossible. This paradox remains unsolvable within relativity's mathematical framework. Therefore, physical time travel is strictly excluded from possibility. However, conscious time regression does not generate any causal paradoxes. When you recall the scene of yesterday's dinner, your act of remembering does not alter the actual content of yesterday's dinner. When you imagine the M78 nebula 1600 light-years away, your thoughts do not affect the true state of that nebula. Consciousness accesses the past in read-only mode. This read-only property ensures the integrity of past history. From the perspective of quantum field theory, the field configuration at every spacetime point is deterministic. These field configurations constitute the immutable history of the universe. Consciousness, as a function of the physical system that is the brain, can only access history indirectly through memory traces. It cannot truly alter the fixed field configurations. This immutability is precisely the manifestation of causality. Modern cognitive science defines memory as a constructive process. We do not retrieve complete video recordings from a repository, but rather reconstruct scenes based on retained characteristic cues. This reconstruction process is significantly influenced by our current knowledge background, and may also be biased by differing emotional states, potentially incorporating entirely fictional details. This constructive nature further demonstrates that consciousness's return to the past is not physical time travel, but rather a creative simulation performed by the nervous system in the present. Considering the perspective of the second law of thermodynamics, the universe's entropy increase defines the direction of the arrow of time. As a function of the brain, an open system, conscious activity likewise adheres to the fundamental principle of entropy increase. When recalling the past, the brain's entropy continues to rise. The energy expenditure of neural activity persistently incurs thermodynamic costs. This process aligns perfectly with the direction of the arrow of time, with no violation of thermodynamic laws occurring. In relativity's mathematical formulation, spacetime is described as a four-dimensional manifold. Each event possesses definite spacetime coordinates. Conscious activity, as a physical process within the brain, corresponds to a specific world line in four-dimensional spacetime. This world line perpetually extends toward increasing time coordinates, and has never exhibited reverse motion. Our perceived return to the past is actually merely the normal extension of the world line along the time dimension, accompanied by specific changes in the brain's internal state. These changes enable us to access stored memory information, but this absolutely does not imply we have truly returned to a historical spacetime point. Understanding this crucial distinction holds profound philosophical significance. It helps us clarify the relationship between subjective experience and objective reality. Consciousness grants us the ability to perceive the passage of time, but the essence of time is defined by physical laws. We can retrace the past through memory. We can foresee the future through imagination. Yet these mental activities all occur within the eternal present. This realization both allows us to appreciate the marvels of consciousness, while also fostering a proper reverence for physical laws. Precisely because of consciousness's non-physical nature in retrospective, it achieves perfect compatibility with special relativity. Simultaneously, this compatibility explains why, no matter how freely our consciousness may roam, we cannot alter objective facts that have already occurred. The reality of history is solidified by the material state of the universe. Consciousness can interpret it and explain it, but it can never rewrite it. This conclusion does not restrict consciousness, but affirms the harmonious coexistence of physical laws and conscious phenomena. Within this cognitive framework, we can fully enjoy the time-space traversal experiences consciousness affords, while maintaining steadfast faith in the fundamental laws of the universe. Human thought possesses boundless realms. The vastness of this inner universe is astonishing. It can hold the majestic vistas of stars and oceans, and trace the long journey of life's evolution. Within consciousness's realm of freedom, we can explore the subtle laws of the quantum world, and contemplate the grand structures of cosmic scale. This infinite extensibility of thought is humanity's most precious cognitive trait. Yet the physical universe has clear boundaries. The speed of light, as the ultimate limit for information transmission, sets an insurmountable boundary for our exploration. No physical entity can breach this limit. This constraint defines the scope of the observable universe, and ensures the integrity and rationality of causality. The free galloping of thought and the strict constraints of physics form a remarkable contrast and complementarity. Though our consciousness cannot travel faster than light, it can comprehend the cosmic law of the speed limit. This fact itself holds profound revelation. Understanding a limitation means transcending its constraints. We know why we cannot exceed the speed of light. We know the physical principles behind this limit. We know how this law sustains cosmic order. This intellectual comprehension is itself a triumph of thought. In a sense, understanding the speed of light limit is greater than exceeding it. For the former requires wisdom's insight, while the latter demands only greater speed. Through the collaboration of billions of neurons, the human brain constructs infinite mental space within the confines of the skull. This space remains unconstrained by the speed of light, enabling us to conduct any thought experiment. We can mentally reconstruct the entire history of the universe. From the Big Bang to its ultimate conclusion, we can mentally deconstruct the smallest particles, exploring the peculiarities of the quantum world. We can even reflect upon our own cognitive processes, studying the neural mechanisms behind consciousness. This capacity for self-reference is the most wondrous feature of the realm of thought. Yet the infinite freedom of thought must be grounded in a sober awareness of physical constraints. Our imagination may reach the edge of the universe in an instant, but our bodies must obey the laws of physics. Our consciousness may traverse time freely, but our actions can only influence future events. This duality of cognition defines humanity's unique position in the cosmos. The history of science is the history of thought continually expanding its frontiers. From Copernicus's heliocentric theory to Hubble's cosmic expansion. From Darwin's theory of evolution to Watson and Crick's DNA. Each cognitive leap redefines the frontiers of thought within the cosmos. We extend the boundaries of vision with telescopes, explore microscopic limits with particle accelerators, describe unobservable phenomena through mathematical models. These tools are extensions of the realm of thought, allowing us to transcend biological instincts, to touch the deeper truths of the cosmos. In this exploration, we gradually realize the greatness of thought lies not in its ability to transcend physical constraints, but in its capacity to comprehend and embrace these limitations. Within these constraints, it creates immortal cultural and scientific achievements, masterpieces of art, music, literature, and science are brilliant flowers blooming within the confines of physical limits. They prove finite life can create infinite value. This realization fills us with both pride and humility, proud that human thought can comprehend the laws of the cosmos, humble that we remain forever part of the universe, subject to its fundamental principles. Within this framework of understanding, we neither belittle ourselves nor indulge in blind arrogance, but with a calm and steadfast attitude, continue exploring the mysteries of thought and the cosmos. When we gaze upon the starry sky, we see not only distant celestial bodies, but the infinite possibilities of human cognition. These starlights have journeyed long to reach our eyes, yet our minds can decipher their meaning, reconstruct their evolutionary history. This process reveals the wondrous resonance between thought and the cosmos. Light's transmission requires time. Mental comprehension happens in an instant. This asymmetry precisely embodies the unique value of human cognition. In this vast universe, humankind may be but a tiny speck, yet our minds can encompass the entire cosmos, understand its mechanisms, and appreciate its magnificent vistas. This capacity grants us an irreplaceable position in the cosmos. Now, carrying this awareness, let us enter a state of tranquil sleep. Let the vessel of thought temporarily dock and rest in the harbor of the stellar sea. Tomorrow, when dawn breaks once more, We shall continue this eternal exploration, seeking greater truth and wisdom between the infinite frontiers of thought and the finite boundaries of the universe. Now slowly close your eyes. Let your breath deepen and steady. You have just completed a magnificent cosmic voyage, from the microscopic universe of your mind to the macrocosm of the galaxy. Now is the time for the ship of your thoughts to gently descend and dock in the tranquil harbor of the starry sea. Feel each point where your body touches the chair or bed. Notice how gravity gently embraces you. You need not ponder the limits of light speed, nor probe the mysteries of consciousness. Simply exist here and now. Imagine your thoughts like a starry breeze gradually calming, no longer chasing distant galaxies, no longer traversing the mists of time. They simply linger quietly in the space of the present moment. All your quests for knowledge and exploration may now rest temporarily. Recall the M78 nebula we discussed. It still glows quietly 1,600 light-years away. Its existence requires no conscious effort to sustain. The universe has operated at its own rhythm for billions of years. Tonight, it will continue its journey, and you may safely lay down the burden of being an observer. Feel your eyelids growing heavy as nightfall gently blankets the earth. Those active neurons begin entering repair mode. Neurotransmitters dim like starlight. The intricate universe of your brain shifts into low-power mode. Your breath becomes the universe's rhythm. With each inhale, starlight seems closer. With each exhale, worries drift farther away. No need for deliberate control. Simply observe this natural cadence. As calmly as watching galaxies spin, consciousness is no longer a puzzle to unravel, but a gentle companion guiding you to sleep. It no longer needs to traverse time and space, only to dwell here and now, synchronized with your heartbeat, dancing with your breath. Imagine yourself floating in a tranquil nebula, surrounded by softly glowing interstellar dust, gently cradling your body. Each breath draws in cosmic energy. Each inhale and exhale releases the day's weariness. Those unresolved mysteries of the cosmos can be entrusted to dreams for further exploration. In dreams, perhaps you may find another way to converse with the stars, to dance with time. But now, simply allow yourself to sink into this precious stillness. Your body remembers how to sleep, just as galaxies remember how to spin. No effort is needed, no persistence required. Only let go of the urge to control. Trust this body shaped by eons of evolution. It knows how to mend, how to restore. Outside the window, perhaps real starlight shines, or perhaps only city lights glow. But now they are both points of light guiding you to sleep. Like night lights the universe lit for you, gently guarding your rest. Daytime thoughts have planted seeds in your mind. They will grow quietly in your sleep. When you wake tomorrow, new insights may naturally surface. But now let the fields of thought lie fallow. Let the subconscious take over this fertile ground. Feel drowsiness wash over you like waves, one after another. Each surge deepens your relaxation, sinking deeper into this comforting state. The universe's mysteries remain forever present, and rest is your most vital task now. Let all knowledge dissolve into starlight. Let all questions vanish like smoke. You need not remember anything, nor understand anything. Simply become a beautiful presence, resting peacefully within the vast cosmos. In this infinite space-time, the most vital thing now is the tranquility you are experiencing. Let sleep gently envelop you, as the universe embraces an ordinary star. In this embrace, release everything. Sink into sweet dreams.